Now look at this circuit. We just have to find the current through the middle branch of the unbalanced Wheatstone bridge. So this thing will be equals to I2 minus IC. So hello everyone, a very warm welcome to LN Overseas. I'm back with the series that is 45 topics in 45 days. And in this series we take 45 topics, 15 from each of the subject. And today we are going to take a topic of physics, and that is the Wheatstone Bridge. So first, it was kind of discovered by Sir S.H. Christie in 1833 and later on improved and popularized by Sir Wheatstone, right. So Christie said that it is a diamond circuit to actually find unknown resistance, right, and Wheatstone actually made a working model out of it. Getting the point? So here we have Wheatstone bridge and we have to understand the same thing, that how we are going to apply the concept of Wheatstone bridge to actually get the unknown resistances and how many different kind of Wheatstone bridges are actually there. So let us begin. So it is a specific combination of resistors in which no two resistors are either in series or in parallel. Basic. A circuit that looks something like this, right. Now this kind of circuit, right, it is looking something like this, but it is not the only one. There could be many different variations of the Wheatstone bridge that you can find. However, the complete mechanics behind it, that will be absolutely the same. Okay, so in this circuit we could be interested in finding the net equivalent resistance, or this central branch is of my utmost importance. Why? Because by using a simple principle, if I make the current through this branch 0, right, then it will be quite easier for me to determine different parameters related to any particular circuit, right. So the applications of Wheatstone bridge could be found in a post office box, yeah, in soil analysis, yeah, absolutely. In the first use dates back to I think late 1900s, where they used to analyze soil using the principle of Wheatstone bridge, right. So let us see, right, let us understand the Wheatstone bridge, and that too by a question. So what's the question? Find R equivalent between A and B. Now look at this circuit. We just have to resolve this circuit somehow. Okay. Now when you look at this circuit, no resistor is in series and neither they are in parallel. So what to do? The best bet is to connect a battery between the points A and B. Yeah, I can do that. The EMF of the battery is E, and suppose the current delivered by the battery, that is I. Okay. Now I have to replace this complete complex looking circuit into one single resistor. That is your R equivalent. Simple. So now what I have to do? I have to make a circuit that looks something like this, where you have a resistor and a battery. This resistor is R equivalent, this is E, and this is current. So from here R equivalent is equals to E by I, right? So somehow I have to calculate the value of E by I. Okay. So let us try and find it out. Suppose the current is I, the current that goes through this 10 ohm resistor is say I1, yeah, and through this it will be I minus I1. Now what you can do, you can divide the current from here. But there is one interesting thing that you can observe from here, that it possesses iosymmetry. What is this iosymmetry? Iosymmetry means even if you reverse the battery, the current distribution will remain the same, right? But it will happen in the opposite direction. So that means if here in 10 ohm resistor I1 is going, I1 will come from 10 ohm resistor, this 10 ohm resistor as well. That's what we get from iosymmetry. So from here we have I minus I1, and they are both going to combine to give you I. What will be the current through the central branch? I1 is coming, I minus I1 is going, right? So this thing will be equals to 2 I1 minus I. This minus this. Yeah. Apply KVL, right? In this branch. So from KVL I can write minus 10 I1 minus 5 twice of I1 minus I. Then we have plus 5 I minus I1, this thing is equal to 0, right? In this loop, check, current is like this, high potential to low potential, current is like this, high potential to low potential, minus minus, current is like this in this case, but I am going in the opposite direction, I am going in low potential to high potential, so it will be positive. Let me just write it in simpler way, simplify it. So this thing will be equals to, we have I1 and I, that is plus 10I. This is minus 10 and minus 5. Minus 25 I1 is equals to 0. So I1 from here will be equals to 10 by 25 I, right? Or 2 by 5 I. Check. Yeah, definitely. Now, what is the next branch that I must choose? This could be this, it could be this, or it could be the complete branch, right? This branch or this loop. What I have to choose? The outer one. Why outer one? Because we have to calculate the value of E by I. We do not want value of E. We do not want value of I. We want value of E by I. Getting the point? So let us select the outer branch. Why? Because E is coming in the outer branch only. Getting the point? Okay. From here, what is the current rule? Starting from this point, we have minus of 10 I1 minus of 5 I minus I1, coming back here, plus E is equal to 0, low potential to high potential, going like this. Check. From here, E will be equals to, this will be minus 5 I, and this will become positive, so plus I1. Substitute the value of I1 from here. So I plus 2 by 5I, right? So this thing is equals to 7I, or E by I is equals to 7 ohm. No rocket science. So whenever you encounter Wheatstone Bridge and they ask you R equivalent, this is what you have to do. Calculate the value of E by I, right? I know what's Wheatstone Bridge in this. So this is unbalanced. This is unbalanced. What is going to happen when it will become balanced? We'll see. Okay. Let us take another example of unbalanced Wheatstone Bridge. Okay. Find the current through the middle branch of the unbalanced Wheatstone Bridge circuit as shown in the figure. So Wheatstone Bridge circuit could look something like this as well. Okay. Now, here I have to calculate the current from the central branch, because central branch is the important branch. So we have 2 volt battery. I can use KVL here, that will give me the result, but that will be lengthy because you will have 3 different, there is no IO symmetry, right? There is no IO symmetry, then you are going to get 3 different variables and 3 different equations. So you have to solve 3 equations to get the values of 3 variables and then conclude about this. So you have to use matrix method or whatnot, isn't it? So let's make things easy. Suppose potential of this point is 0. I can do that. Potential of this point will be 0. What will be the potential of this point? 2. Right? Right. Now, say potential of this point is x. Yeah. Sir, but if x is higher or lower? Assume that it is maximum and apply KCL across it. So there will be 3 currents that will be going like this: I1, I2, I3. So if this is at the maximum potential, highest potential of the circuit, I1 will go here, I2 will go here, I3 will go here, right? So from KCL, I1 plus I2 plus I3 is equal to 0. Agreed? Yeah. What is I1? Potential of this point is 2, right? So this will be x minus 2 over 1. Yeah. What will be I2? Suppose potential of this point is y with respect to x. So this will be x minus y over 4 plus x minus 0 over 2, right? Take the LCM, make the equation. So you have 4x minus 8 plus x minus y plus 2x is equal to 0. So how many x are there? 4, 5, 6, 7. 7x minus y minus 8 is equal to 0. That's the first equation. Only 2 variables. Getting the point? Only 2 variables. What about the next? Now forget about this thing. Now suppose y is at the maximum potential, right? Now again there will be 3 currents: I1, I2, I3. Again I1, I2, I3 will be equal to 0. What will be I1? That will be y minus 2 by 2 plus y minus x by 4 plus y minus 0 by 3. This thing must be equal to 0. LCM would be 12. So 6y minus 12 plus 3y minus 3x plus 4y. This thing is equal to 0. Yeah. So 6 plus 3, 7. 7 and 4, sorry, 13. Right? 7 plus 4, 6 plus 3, this will be 9. 9 plus 4, 13. Yeah. 13y. Right? Keep on checking. Minus 3x minus 12 is equals to 0. That is my second equation. Now what we have to do? We have to solve it. Right? Multiply this thing by 13. Right? So 1 into 13 minus 2. That's what we are going to do, right? I'm writing it in the same page, so it will be clearer to you. So this will be 1 and 91 x minus 13y minus 4 104 is equal to 0, right? Yeah, multiplied by 13, then minus 2, so minus, not minus, plus 2, right? Because y is in negative here, so y is in positive here. I will be eliminating y. So from here this will be minus 3x plus 13y minus 12 is equal to 0. Add them together. So this gets cancelled. What will have? This is minus, right? Minus 3x. So this will be 88x is equals to, right, whatever we will get, this will be 6, right? 6 116, right? 116. So from here x is equals to 116 by 88, right? If you cancel it out, this will be 5, this will be 8, and this will be 4. Again you cancel it out, this will be 22, and this will be 29 by 22, right? So we have the value of x 29 by 22, right? Take any equation, substitute. So let me choose this equation, 7x minus y minus 8. 7x minus y minus 8 is equal to 0. So this will be 7 into 29 by 22 minus 8 is equals to y, right? So this thing will be equals to, this will be 3, and this will be 14, and 203 minus 22 into 8, right? 22 into 8, so this thing will be equals to 176 over 22 is equals to y, right? So from here if you subtract, you are going to get, this will be 4, 24, 27. So y is equals to 27 by 22. So what is the current through the central branch? Current through the central branch, that is x minus y by 4, right? I2 is x minus y by 4. So calculate it, x minus y by 4. So x is 29 by 22, y is 27 by 22, right? X minus y by 4 is the current through the central branch divided by 4. So this is 2 by 22 into 4, 11, or 1 by 44, 0.022 something ampere. Getting the point? So if you encounter any Wheatstone bridge that is unbalanced, you have to use KVL or KCL depending upon the situation, right? But what is this balance unbalance? Let us talk about that thing. So suppose current from this battery is I. Here you have, suppose current I1, here you have I2, here you have, say, IC, right? IC. So this thing will be equals to I2 minus IC, right? This thing will be equals to I1 plus IC, and finally you will get I1 plus I2, which is equals to I, right? I will be equals to I1 plus I2, right? Apply K. KVL from here. So minus I2 R2 plus I1 R1 and minus IC R5, this thing must be equal to 0, right? For the first case. For the second case, again apply KCL. So this will be minus R4 I2 minus IC, then plus I1 plus IC into R3, then plus IC into R5, this must be equal to 0. Now if I say that the current through the central branch is 0, current through the central branch is 0, that is IC is equal to 0, then what is going to happen? Let us see. IC is 0, right? IC is 0, IC is 0, IC is 0. From the first equation, what you have? I1 R1 is equals to I2 R2, which means I1 over I2 is equals to R2 over R1. From the second branch, what are you going to get? Minus R4 I2 plus I3 R3 is equals to 0, right? If IC is 0, then I1 R3, right? I1 R3. So from here, I1 by I2 is equals to R4 by R3. Equation 1 and equation 2 LHS is same. That means R2 by R1 is equals to R4 by R3. Right? R2 by R1 is equals to R4 by R3. So if I have to make the current through the central branch as 0, what is it that I have to do? R2 by R1 must be equals to R4 by R3. Right? If I make the ratio same, the current through the central branch will be 0. And that is the condition of the balanced Wheatstone bridge. If this thing doesn't match, then it will be unbalanced Wheatstone bridge. So this is a specific case. This is a specific case of Wheatstone bridge where it is balanced. Getting the point? So let us take a question. Find current through the battery. Current through the battery. That means we have to find an equivalent circuit for this. Okay. Now consider this much part of this circuit, right? In this part, look at this much part for now. Okay. So here you have 1, you have 2, here you have 2, here you have 4. Is this a balanced Wheatstone bridge? So ratios must be same, right? So 1 by 2 is equals to 2 by 4. Yeah, this is true. So that means this is actually a Wheatstone bridge. Then that too a balanced Wheatstone bridge. So that means the current through the central branch is 0. That means this is redundant. This is redundant, right? What about now? Now this circuit is pretty simple. So here you have 2, here you have 4, and here you have 1, and here you have 2. Now these two are in series. So what will be the equivalent? 3. These two are in series. What will be the equivalent? 6. And this 6 and this 3 together, this 6 and this 3 together, they are in parallel. They share the same 2 points, right? The potential difference across them will be absolutely the same. So what will be the equivalent of 6 and 2? That is 6 and 3. That is 6 into 3 divided by 6 plus 3, right? And that is 2, isn't it? 9, 3, 2. Yeah. This is our equivalent for this thing, this complete yellow thing. Now, the circuit will look something like this. This is 6. This is 2 that we have just calculated. This is 16. This is 12. This is 4. Right? And this is 2. Right? The circuit is something like this. Again check for the same thing. 6 by 2. 6 by 2 is equals to 12 by 4. True. True. That means there is no current through the central branch. Right? Now that is easy. Now what we have to do? Now from here, these two are in series, 6. These two are in series, 18. And these two together, they are in parallel. So what will be R equivalent for this case? R equivalent will be 6 into 18 over 18 plus 6. This is 24 or 4, 9 by 2. 9 by 2 or 4.5. Right? So now this complete circuit is now 4.5. So what will be the equivalent circuit now? This tiny small little circuit with no problem at all. You can solve this circuit quite easily. So 4.5 plus 2, they are in series. 6.5 is the resistance, right? Net resistance will be 6.5. And what will be the current? What will be the current? Current will be equals to 6.5 divided by 6.5. That is 1 ampere. Oh, at last 1 ampere. So easy. Looks overwhelming, but by the concept of balanced Wheatstone bridge, quite easy. You just have to apply it again and again. So that's how you have to tackle the questions of unbalanced as well as balanced Wheatstone bridge. So this is it for today. I hope you have enjoyed this session. So you can continue watching the series. The link is available in the description box. And if you have any queries, any doubts, any questions, you can drop it in the comment box. So thank you. Have a nice day ahead.